So it is my great pleasure to introduce Kim Baraka. Kim is currently a postdoctoral fellow at the Socially Intelligent Machine Lab at the University of Texas in Austin. He's a dual Ph.D. in robotics from Carnegie Mellon University and Instituto Superior Técnico in Lisbon. He also has a master's in robotics from Carnegie Mellon University and a bachelor in electrical and computer engineering from the American University in Beirut. So he went all over the world. His research lies basically in the intersection of artificial intelligence, machine learning, and human-robot interaction, and is interested in developing computational methods for transferring information and knowledge between humans and robots. Kim will be joining the Vrije University in Amsterdam pretty soon as an assistant professor. And as I said before, he's a professionally trained dancer, contemporary dancer. So if you have any questions, also ask them about that. So having said that, Kim, take it away.
Thank you so much, Miguel. Thank you for everyone, for organizing this and for trusting me to give this presentation. I'm going to go ahead and share my screen. If you have any trouble seeing, please do let me know. But you should be able to see my slides right now.
Perfect.
Great. So thanks again. This is really a heartwarming opportunity for me because I'm not only able to share the kind of broad research vision that I have, but I'm also able to do so with some really special friends of mine that I miss dearly in Lisbon and all around the world. So today I want to talk to you about this kind of broad perspective on my research. So you shouldn't expect too many plots or too many formulas, but a lot of videos. So hopefully that will get you engaged throughout the presentation. So the title of my talk is Robots and Humans, Teaching and Learning Through Social Interaction. And in a way, this is my attempt to tell you the story of my research, going from my master's thesis work all the way to my planned work as an assistant professor this coming year. So what I'd like to do first is to take this title and kind of dissect it a little bit, starting with the first word in this title, which is obviously robots. That's what this podcast is about. And so throughout my research, I've worked with a number of robotic platforms ranging from mobile service robots all the way to manipulators, including haptic devices. And each of these platforms present challenges in robotics and in AI that are different, right? Because they have different capabilities, they have different embodiment, they have different precisions. And what I'm interested with these robots specifically is their interactions with people, right? And when we say people, typically, most of typical research will consider people as this average user kind of person, right? A model that works for most humans. But there are as much as there's diversity in robots, there's also diversity in humans, right? And so throughout my research, I've actually not just worked with what we call an average user, but I've also considered special types of people or special types of humans, such as children, therapists, but also dancers and choreographers and visual artists. So before I talk about teaching and learning, which is the focus of this talk, I'd like to talk about a necessary but not sufficient condition for learning and teaching, which is communication. So communication is a big word, right? And with robots, we try to think, how can robots communicate to people in a way that is similar to how people communicate with each other? And this is actually the first robot that I worked with ever during my master's thesis. It's called the Cobot robot. It's a mobile service robot that goes around the buildings, takes the elevator, takes objects from place to place. And as you realize, this robot has no arms, right? So you may wonder, how does it take the elevator? How does it pick up this mug here shown on the right? The secret with this robot is that it interacts with people in what we call a symbiotically autonomous way, meaning that when it faces limitations, it's able to ask for help from people. And so people in its environment gladly are able to help the robot overcome its limitations. Now, this robot looks a bit dumb, right? It's a computer on wheels, right? It doesn't have much expressivity. It has a screen that it can use. It actually talks, but something was missing. And so the work that I did during my master's thesis was focused on finding ways that these robots could visually communicate what's happening inside their algorithms, inside their their state machines, their MDPs, whatever is going on inside the robot needs to be somehow externalized to people, right? And so we used LED lights. You can see one along the column of the robot and another one around the base to communicate different types of states of the robot, such as being blocked by an obstacle, communicating navigational intent, and so on and so forth. So why is communication important, robot to human communication specifically? What I'm showing on this slide is actually a different type of robot. It's an autonomous car. And this screenshot specifically is a screenshot that was taken from a video that's available online a few seconds before, a few splits of a second before this car hits the person in front of it. And the reason why it hit the person is because the autonomous braking system actually failed. And you can imagine that the impact of communication here is crucial. Had the car communicated to the person that it did not detect their presence, or that it was not going to be braking in the next few seconds, but actually accelerating, then the person could have saved themselves an injury. Great, so now that we have established the importance of communication, I want to sort of try to define what communication means in terms of AI concepts. The way I see communication is a transfer of information between two agents. And agents here can represent either robots, robotic agents, or human agents. Now, if we want to go into teaching and learning, we're not just talking about transfer of information, we're also talking about something a little bit broader, which is transfer of knowledge or transfer of skill. So if you think about a robot, transferring information in the case of COBA would be making the state visible, right? Saying I'm in state X, basically a variable, right? And this variable can be as complex as you want it to be. But a knowledge or a skill is actually a program, right? It's a policy in an MDP, right? Or it's a plan in classical planning. And that's where I think the difference lies. So the last part of my title is this idea that the teaching and learning doesn't happen in a sort of mechanical form, right? It happens specifically through social interaction, through interactions that are natural and that are human-like. And I'm listing here a few of the plethora of modalities that people use when they teach, whether they're teaching children or they're teaching animals. I think we can actually draw inspiration from both types of teachings. So in this talk, what I want to talk about is two things. In the first part of the talk, I'm going to talk about robots teaching humans. And in the second part of the talk, I'm going to talk about exactly the reverse. Specifically in the first robot as a teacher paradigm, I want to talk about two types of humans that the robot's going to teach. The first one is obviously a human learner, a human that is typically learning in the context of an interaction. But I'm also going to focus on robots teaching humans that typically have the roles of teachers, and you'll see how that's going to happen. And in the second part of the talk, I'm going to reverse that big arrow, and we're going to talk about some interesting algorithmic contributions. So starting with robots teaching human learners. During my PhD, during my time in Portugal, actually, during the 2 years of my PhD in Portugal, I was collaborating with this Center for Development or Center for Child Development, where I worked with children with autism. And the goal was to bring robots to help these children acquire specific social skills that are more or less building blocks of more important social interactions with people. And so for the sake of illustration, I'm going to talk to you about specific tasks that we considered, and then I'm going to talk about some algorithms that we developed within these tasks, but that can also generalize to really any task that involves the same kind of structure. So the main focus of these interventions with the robot were to work on attention skills. And by attention, we mean that the gaze of the child, or where the child is looking at, could be, let's say, looking at the robot or looking at one of those screens that we had in our scenario. So in the first task, the goal of the robot is to direct the attention of the child from the robot to one of the screens, and we call that the joint attention task. And when you want to reverse that, so directing the child's attention from the screen back to the robot, by calling their name, we're calling this the name task. And so the first step was to design an action space for the robot. And I'm showing here different actions by increasing level of specificity or increasing level of assistance, where the more information or the more stimulus we give, the more you're helping the child. And this is actually inspired by the ADOS manual, which is the gold standard for autism diagnosis. So what was the algorithmic challenge here? Think about an adult helping or teaching a child how to ride a bike, right? What happens if you under-assist the child? Well, the child's gonna fall, right? That's gonna be a task failure. And what happens when you over-assist the child? That's also gonna be a failure because you're not gonna be challenging the child enough, right? You're not gonna help them learn. They're just not gonna be learning. So somewhere in between these two extremes lies the just right level of assistance. And this is what we wanted to kind of formulate mathematically to be able to apply it to specific scenarios that are social in nature. And those are examples of robots that have been introduced in a variety of socially assistive contexts where we could apply this kind of thinking. So to give you a different example here, I'm showing a hierarchy of 10 different actions of increasing levels of assistance in the context of speech therapy. So given a list of actions, or given this hierarchy of actions, the question we ask here is, how should a robot sequentially adjust its level of assistance, knowing that there might be potentially multiple trials until the child or the learner will respond in an appropriate way? So how do we think about this algorithmically? The first concept is to introduce this idea that these actions are actually ordered by increasing success probability, right? The more assistance you give, the more probable it is for the task to succeed, for the learner to actually respond in a correct way. The second key aspect here is that these actions are actually costly, right? Because the more you help, the less you challenge the child, and so the less the child will learn. So these costs are really therapeutic costs. The third assumption here is that when the patient or when the learner achieves the goal, right, we get a high reward, right, which is a negative cost. And we're going to call this reward capital R. And that really depends on the task. So it's really something that is domain dependent. So now that we have these parameters, the question becomes, can we generate quote unquote optimal action sequences? And what we mean by optimal is we're trying to minimize the expectation over the total cost of sequences. Let me show you practically how that works. So what the robot will be doing will be generating what we call an optimal action sequence. And this is the formula for it. I don't need to go into details, but it's basically a dynamic programming. It's an optimization problem that can be solved with dynamic programming, where this optimal sequence that the robot generates is basically a sequence, an action sequence that can provably minimize the average cost over multiple children, knowing that, you know, every child will respond differently, right? So some children will respond upon the first trial, others will respond at the very last trial, capital T here, right? And this is a algorithm that is linear in both the number of tasks, or sorry, the number of actions, and the time horizon that we denote capital T. If you're interested in the details of the algorithm, I invite you to look at this paper. I'm including QR codes, so you can just pull up your phone and then you'll get the paper directly. Great, so how are we able to generate these action sequences with the actual kids, right? So the first thing we did, going back to the study that I was talking about, was to collect data with these children. And we had two conditions. In the first condition, the robot follows this plan or this action sequence that has increasing levels of assistance. And the goal of this is to categorize the children into 4 different level of impairments, from high response all the way to minimal response, like a therapist would typically diagnose these kids. And in the second condition, we had a completely random action sequence that would allow us to gather data that is free from any order effects. And based on the data we collected, we basically run a logistic model over the interaction data, and we're able to estimate these probabilities as a function of both the action level, but also the level of impairment of the child. So now that we got the probabilities of success, the second part was to think about how to estimate these costs, right? We talked about therapeutic costs. So what it meant in the specific context is that, well, costs can be approximated as level of explicitness, right? So the more explicit the robot in communicating what it's expecting from the child, the more costly therapeutically these actions are. And so what we did is we basically, we recruited a bunch of psychologists and we showed them the videos of the robot, and they rated how explicit on a continuous scale they thought the action of the robot was. And then we gathered the data, and then bam, we have costs, probability of success, and then we just plug them into the algorithm. And the algorithm is able to generate, as you can see, different action sequences for different children profiles or different impairments of these children, which means that it's able to personalize these action sequences according to the needs of every learner. And here I'm showing the same on the different task, where you can see that the plans are actually different for different tasks. What we actually were able to do in this paper is to prove that these sequences, these optimal sequences, are always non-decreasing, which actually aligns with the way that teachers or therapists in this case interact with these children in these contexts. And if you're interested in extensions of this algorithm that are not linear, you can look at our journal paper, JMAS, that considers different types of dependence on history. All right, so I apologize if this was a little bit dense. I promise that from now on, it'll be more high level. So we've talked about robots teaching human learners, right? What I'd like to talk about now is robots teaching human that are typically teachers. And in this context of autism therapy, teachers are therapists, right? And so I'm showing here an interaction between the same now robot, but instead of interacting with a child, the robot is interacting with a therapist. And you may ask why? Why would a robot want to interact with a therapist? The answer is that this robot was used to help train therapists perform certain interactions that are standardized in a better way. And in this case, we looked at diagnostic. The way that the autism is diagnosed is actually through interaction, through social interaction. And so the goal here is that through interacting with the robot, these people, therapists, will be able to perfect their skills and then apply them to actual interactions with children. So even though when you interact with a child, you're in a kind of context where you have no room for errors, you're limited by real cases, and it's a one-shot kind of interaction, with a robot, what you're able to do is to train those interactions in a context that is error tolerant, diverse, and also repeatable. And so we developed an architecture for what we call robots with quote unquote autism-like behaviors, where we had a bunch of features that we could control, and this controlled how the robot responded to specific standardized stimuli or tasks. And so you can see here that the robot is using its body, is using different gazing patterns, is responding to speech, is using gestures like pointing. This is an example in this specific snippet of the video of a low severity of autism. And then I'm showing the exact same interaction, but now the robot is responding in what we call a higher severity of autism. So here, for example, the robot is only responding to touch and is not responding to voice when the person calls their name. Or in this joint attention task, the robot doesn't respond to pointing and gazing, but only responds to the sound of the bottle being hit. And this was apart from a few parameters that were hard-coded, this was an autonomous system that you could interact with according to these standardized prompts that you could use. Not going into too many details about the method, but the general idea was that the way we were able to achieve such a system is to really exploit the structure of these interactions, right? And if you look at this manual called the ADOS2, this is basically a recipe for therapists to interact with children, right? It's as if the therapists have an algorithm that they have access to, that they're able to apply to be able to assess behavioral features of these kids in a standardized way. So what we did is we took that pipeline that the ADOS gave us, and we said, well, what if we just reversed it? So what if instead of going from behaviors all the way to severity values, which say this child has mild autism or severe autism or no autism, what if we start from the severity metric and we climb our way back up to generating behaviors? And this is an underdetermined problem, right? There are many behaviors that fall under these same high level classes. So here, all the science work was about how to actually pick and sample these behaviors. And if you're interested, this this APIA paper talks about the process, and this ICDL paper talks about the data-driven approach that we use to sample feature vectors. All right, so this was kind of a little bit fast, but this was in a few minutes what my PhD thesis was about, which is basically in the first part, having robots teach human learners, focusing specifically on this idea of personalized teaching. And in the second part, having robots teach human teachers, right? Or humans who are typically in the role of a teacher when interacting with humans. And specifically in that case, the contribution was focused on teaching through mock-up interactions. So this concludes the first part of my talk. In the second part of my talk, I'd like to just switch things over their head, right? So basically now what we're doing is that we're having a human be the teacher, and we have a robot that's going to learn from humans. And even though, you know, these on the slide that look the same, the types of challenges and the types of methods that are going to be used are drastically different. And so to motivate this problem of humans teaching robots, or conversely robots learning from people, I'd like us to take a minute and just watch a video that I find extremely interesting. And it's interesting maybe for different reasons that you might expect, but I would like you to observe this interaction very closely between an opera coach and an opera singer. And then we can discuss this afterwards. So I'll just stop talking for now, and then we can listen to this. Let me know if there's a problem with the sound, but I think it should be fine. All right, so let's watch this.
And yes, yeah. Up here.
All right, so this is probably an example of, I think, one of the best teaching interactions I've ever experienced. You realize that people are clapping in the end, right? And I think they're actually clapping more for the teacher than they're clapping for the learner. But that being said, I think both of them are doing an amazing job, right? So if you look at how this teacher is using all possible modalities to provide these instructions and to provide this teaching experience to the learner, they're using metaphorical gestures, right? What is this thing? What is this metaphorical gesture? How does it relate to an actual control algorithm in the vocal cords of the singer? Using evaluative feedback. Yes, no, more of this, more of that, using what we call advice. So all of these different ways that the person is interacting with different modalities, right? So with gestures, with touching, right? Like that moment where she's touching the face of the singer. So this is, I think, kind of an inspiration for what we do in robotics. The truth is we're very, 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 very far from this, right? This is what interactive robot learning typically looks like. And when I say interactive robot learning, I mean machine learning algorithms that are implemented on robots where people play a role in the learning process, right? So when I say interactive, I mean human interactive. And those are examples of algorithms that have been developed where people are giving different types of instructions, including demonstrations, evaluative feedback or critique, advice, which can be action advice or other types of advice, as well as corrective feedback. And all of these, and I'm giving examples of algorithm here, but all of these algorithms are, available. They work pretty well in simulation. The problem is that these algorithms have the following interfaces. Most of them, specifically the last three, consider that the human is providing a unidimensional source of information, right? Yes, no, rating or a slider, right? Up, down, left, right, things like that. So it's really, really limited in terms of the information that the teacher can give. And this is why these algorithms are very inefficient from a sample complexity point of view. What we argue is that humans are actually not just a source of unidimensional information, they are a source of rich know-how that can be communicated not only through explicit, but also through implicit signals, right? And I think this opera coach is a prime example of a person who uses a lot of implicit signal, right? All the expressivity in her voice, and so on and so forth. And so I'm showing here an ongoing project that some colleagues at UT and I are doing, where we're looking at extracting a little bit more from speech than what typical interactive machine learning algorithms do. And specifically, we're interested in ways that people use voice to communicate through prosody. And I'm showing here a very simple grid world scenario where this agent here shown in yellow needs to go to the nut and then give it to the squirrel while avoiding the bomb, right? So a very simple task. And the person needs to teach the robot what to do, right? Knowing that the robot doesn't know anything about the environment in the very beginning. So I'm going to show you a little interaction. Here we asked people to have kind of free form speech, so they were not restricted to any particular words. But I'd like you to just focus on how the person is talking to the agent.
Up, 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 up. No. Up. No. 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 Okay, right. Keep on going. Right, right, right. No, 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 right. Up, 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 down.
So even though the person is using, a limited vocabulary of words, you can see that depending on where the agent is and what they're doing and how the person has been interacting with the agent in the, few moments before that utterance, that the way they're saying no or down or yes is really different. And so we argue that how one speaks is as important as what one says. And we argue that we can extract information from the prosody to be able to accelerate learning and to generate richer sources of information that can be used for the learning process of the robot. Another project along these lines that is also under progress or in progress is this idea of using multiple modalities of naturalistic teaching. So here I'm showing a system that some undergraduates and I have been working on for the past few months, where there is an initial demonstration phase that I'm showing here, where we're using this marker-based system. Here the person is moving a ball in space, and this is controlling the end effector of a robot. And so the idea is that you start by showing a trajectory, and then you interact with the robot to refine these trajectories. And so I'm showing here an example of gestures that we are using to control the robot's behavior. And also here, this is an example of how the robot is responding to speech interaction. So here the person is saying, let's see if we can get this to run.
Down.
So the person is interacting through speech, and then the robot is responding according to that. And kind of the broader vision of this project is to have robots that are able to use more than this, so more than gestures, speech, and so on, but use maybe full body demonstrations or full body expressivity, including facial expressions, for example, or to use kinesthetic, not demonstrations, but also interventions, right? And this is how actually ballet teachers correct ballet dancers. That's the most effective way of just touching the right joint, and then the person just instantly knows what they're supposed to do. So I've talked about kind of my idea about how I would like to have robots learn in the future. But I think a more fundamental question we should ask is, what can a robot learn, right? There's an immense array of tasks that a robot could learn. And most of the work that has been done to date in this research area has been focusing on very specific goal-oriented tasks. And I'm showing here handovers, I'm showing pouring, I'm showing ball shooting. And these have increasing levels of complexity, right? Some of them are trajectory agnostic, others really depend on the exact trajectory. But I'm also interested in more open-ended tasks. So here I'm showing brush strokes, which is still kind of a very mechanical kind of thing. But once you apply it to a creative, collaborative painting setting or a dancing or expressive motion setting, things become a little bit more complex, right? And so the claim here is that different tasks call for different interactions, so different modalities of providing the teaching instructions, but also different learning algorithms. And so this leads me to kind of the open research questions that I'm excited to tackle in the next few years. The first one being, how can a robot learn from multiple types of directions or from multiple interaction modalities? And that's kind of what I've been hinting at in the past few slides. The second question is, how can a robot adapt to teaching style? So if this amazing opera coach came and taught my robot, or if an animal trainer came and taught my robot, or if a school teacher came and taught my robot, or if a complete newbie in terms of teaching came and taught my robot, would the robot learn the same? Can the robot change the way it's learning to actually benefit the most from these different teaching styles? The third question I'd like to ask is, how can the robot have an active role in improving the quality of human teaching? And that can happen through feedback, right? Through, I understood what you said, or can you please clarify, right? We're talking about active learning here. But also instructions. So kind of like, okay, you've taught me this, but I already know this. Can you please tell me this other thing? Or can you please change the way you're teaching slightly to help my learning, right? So kind of closing the teacher-learner loop here. And finally, how to learn more open-ended or evolving tasks, right? Tasks that are non-stationary, that are highly interactive. And I'm showing here examples of tasks where the robot and the human are collaboratively, at every single moment, they're collaboratively making a decision, right? On the left, I'm showing a project that I did with some dancers in Portugal where people were doing contact improv with a Baxter robot. And on the right, it's kind of the same idea. There's this collaboration going on in continuous action space and in real time. But what's happening is that the human and the robot are collaboratively painting. So how do these algorithms translate to these more complex, creative, and open-ended tasks? And kind of, the more general question, I think, which is something that maybe will guide the next, I don't know, maybe I won't be alive by the time we have an answer to this question, but how can humans and robots co-learn from each other and also from the environment over extended interactions and extended periods of time? So to end, I would like to show you two pictures. On the left, I'm showing an example of a long tradition that humans have of trying to tame and teach and control animals, right? And this is kind of what we've been doing with robots so far, right? There's actually an algorithm called the tamer algorithm. And on the right, I'm showing snippet from an amazing documentary that I would definitely recommend watching if you have not already. It's called My Octopus Teacher, and it's on Netflix. So if you haven't watched it, please watch it tonight. What's really amazing about this documentary is that this person visits this octopus on a daily basis for over a year. And this octopus ends up giving the person life lessons, from the most basic things all the way to the most deep and emotional lessons. And so the very, I would say, philosophical question that I would like to leave you with, and unfortunately, I don't have an answer for it, is what can robots teach us that other humans probably can't? So I'll leave you with this. I would like to end with acknowledging my collaborators, supervisors, and advisors. This work is collaborative in nature, and so I wouldn't have been able to talk to you about so many projects if it weren't for them. And with this, I'd like to end by letting you know that I'm actively looking for a PhD student. So if you're interested in doing a PhD, if you're interested in interactive robot learning, and if you're interested in living in Amsterdam, then shoot me an email. Thank you very much, and I'll be happy to hear any thoughts you have, comments, or questions. Thank you.
Thank you, Kim, for the wonderful presentation. I think I invite everyone to thank Kim as well. So now we open the session for questions. So if you have any question, please just raise your hand and talk or put in chat. and we will read out for you. So don't worry about that.
I have a question.
Sure.
Glenda, go for it.
Yes, thank you. It was really a great presentation, especially also for me to get an insight on the more technical side. I'm very sympathetic to this, also this last part about the arts and creativity and what can we really teach robots. But I also found it quite interesting that you said, yeah, maybe we can teach them some more complicated or abstract tasks, dynamic tasks maybe. And for me, it's a bit funny because when you go into these kind of creative arts groups, and this is maybe a bit, maybe my naive understanding, but I connect that maybe not so much with task, but expression. So when you dance or you make these paintings, it's also a lot about expressing or making other people see the world or feel the world like you do. And that would require, of course, that there's some kind of someone who can express something, maybe an inner life. And what are your thoughts about that? Would that, is these things something you have thought about? Because with learning, you can also say, but there's knowledge, but does that necessarily lead to understanding? So these more philosophical questions.
Absolutely. Thank you, Glenda. I think you raise a few very interesting points, and I think all of those, when I was doing my slides, I thought about, is there going to be a philosopher in the audience? Should I put an equal here, or should I put an approximately equal here? Should I put a quotation mark around task? And sometimes I did. I said, learning is approximately equal to inter-agent transfer of knowledge and skill, but it's definitely not that only, right? There's definitely more depending on who's learning, how they're learning, what's the context. Same thing for task. When I wrote open-ended tasks, I wanted to put a quotation mark around tasks because, as you're mentioning, task and goal often come hand in hand, right? I do think there are non-goal oriented tasks, but I think tasks are specifiable, fully specifiable. When you think about these algorithms, the way that typically the environment is modeled is through a Markov decision process, right? And the Markov decision process has a reward function, and typically this reward function defines the task. And it's, it's usually really hard to specify reward functions. But when you talk about expression, there's this other way of doing reinforcement learning where there's what we call intrinsic rewards or intrinsically motivated reinforcement learning. And so I would say from an algorithmic perspective, maybe this is what we need to look at for these more open-ended or expressive tasks, is to look at maybe other ways to reward or penalize behaviors that are not just based on an extrinsic definition of rewards. And maybe there are much more complicated ways that these rewards might be generated with maybe more cognitive architectures and all sorts of things. But I do agree that perhaps the terminology needs to change when we look at more than just manipulation or navigation tasks, and we look at these really, involved tasks with people that account for all these complex ways that we behave. So thank you for raising those points. Those are definitely very relevant.
Can I ask an extension of that question, maybe?
Absolutely.
So, let me switch my video so at least you can see the face of the person asking the question.
I'm seeing you.
The question of the sort of the task and what you might learn. There was something, there's sort of an implicit dualism, I think, in your representation of the relationship between sort of task expression and something like opera singing, for example. That's a fundamentally embodied activity. Whatever you're learning is not purely cognitive. I mean, robots don't have a voice box. They don't have emotions. They don't have a voice. They don't have lungs. They don't have a diaphragm. it's not, so we're not just talking about the mental process, we're talking about an embodied activity, and sort of the emotions and everything are tied to that as well. So to me, the idea, I mean, as interesting technically as the challenge is, the idea that that's something that a robot could learn in any meaningful way is doubtful.
What do you mean by meaningful way? Because I think the first part, the first answer to your question that robots are embodied is that those policies typically are, well, I mean, if you're trying to learn how to control your voice, that's a really complex actuating system, right? But I would argue that in theory, the theory behind it is very similar to learning a control algorithm for a simpler actuator system, let's say an arm or some other actuator. But when you talk about meaning, I think there's another layer that you're referring to, right?
Well, no, I mean, robots are disembodied. People are embodied.
I see. And by embodiment, do you mean simply physical?
Well, I mean, it's not just a mind and a body. You see, singing, learning how to sing is not a cognitive task. It's an embodied activity.
Right. Right.
It's not meaningful if you do not have a body. There is nothing to learn there if you do not have a body.
Absolutely. And I think that's a kind of long-standing question, right? With the dualism of robots and the, you know, other theories of how human intelligence works, and people, you know, talking about closing the sensory motor loop and whatnot. But I think for the types of algorithms that we have available now, it is very much, as you were saying, disembodied, right? So you have a control algorithm or a policy that is basically a mapping from states to action, right? It's purely virtual, it's purely cognitive. And then this translates into executing these policies. And of course, sometimes there's an interactive component, there's replanning, all of that, but it's definitely, there's a layer of abstraction of the body as being this mathematical entity. So I don't know what your thought will be on how we could make robots more embodied, or if you're just saying that these are intrinsically different and that we should not draw comparisons. So I'm not sure what your message is.
I am essentially, which I realize is not constructive.
Oh, absolutely not. I mean, I still think we can be inspired, right? And I'm not, the goal is not to replicate that, right? But it's to be inspired and to make those systems more usable from a very practical point of view, because we as humans use these mechanisms to teach. And so if robots can pick up on them and interpret them in a way that is meaningful, or I would say relevant or helpful for their learning, whatever the learning performance is, then I think we should go for it. That's my view.
Well,
but thank you for
your answer.
Yeah, thanks.
So Nezia has raised your hand, so go ahead.
Yeah. Can you hear me?
Yeah.
Okay. Thank you for, it was very nice presentation. So my question is about your first study, like the one you showed at the very beginning of the presentation. It's about like just giving just right help to the autistic kid.
Yes.
How did you test this? Like, how did you make sure that it was just right amount of help?
That's a great question, actually. And it's something that we didn't get to fully test because of practical reasons, mostly recruiting kids again, because we did this first study where the goal was to collect data to estimate these parameters, this little PA, this little CA. But then as you're saying, the goal is to actually show that it works. So what we did is we tried to do this one-shot thing where I only talked about two conditions here. I showed the assess condition where we wanted to kind of build a profile of a child, and then we had a random condition which was used to do estimation. But we actually have a third condition which, before the algorithm was developed, we thought was the best thing to do. And the way we did it is that we took basically the level at which the child responded. This is how these are defined. 1, 2, 3, 4 basically means that on average, the child responds to 3 satisfactorily. So we started with this one, and then if that didn't work, then we increased by one step. And we developed this in conjunction with therapists. So they kind of told us, I think this is what should work based on how I do it with children, based on the manual. So we developed like a mock-up, oh, assist me, which is what our algorithm was supposed to do. And we did test that, but we did not get to test the actual optimal. The hypothesis is that the optimal will perform even better than the version that we did. What was surprising though is that it seems like randomness seemed to matter a lot, because those are attention tasks. And so if you show a lot of entropy or a lot of randomness, that helps the child respond. And so actually this explorer condition, which we thought was going to be the worst, was actually not the worst. And so this is why then when we extended this algorithm, we looked at what we call repetition sensitivity, which means that maybe children actually don't respond in the same way if you've repeated that action before versus if you have not repeated it before. And we did an analysis of all these different cases. And you can look at the paper if you're interested in the model. Okay. But you're right, it needs to be validated specifically with these children. But I would argue that any task that has those particular metrics of success, a probability of success and a cost, lends itself to using these methods. And so, yeah, it could probably be validated in different ways, maybe online or something like that.
Okay, thank you.
Thank you for your question.
I have a question, if it's possible.
Go ahead, Francisco.
Yeah. Okay, so first of all, thank you for the presentation, very, very comprehensive. At a certain point, you were talking about modalities through which experts can teach robots particular skills, and you show a very plethora of different alternative modalities. I mean, modalities, not standardized modalities that you explored. And by looking at that, I thought about this. So would you say this teaching techniques, would you rather see them improving something that had already been learned through a more standardized learning from demonstration technique, if we can allow ourselves to talk about a standardized learning from demonstration technique? Or do you think that these modalities would have the potential to replace more standardized learning from demonstration techniques from scratch? So would you think, from zero, would you be able to use these modalities to teach, or would you build upon something that was already existent?
So the paradigm here was to, as I'm showing here, to first show demonstration and then to apply transformations to it, and then maybe go back and then do this loop again. So I think typically, it has been shown in the machine learning literature that seeding any reinforcement learning algorithm or a interactive reinforcement learning algorithm with a demonstration greatly improves learning. Now, the problem is that demonstrations are often hard to give, right? Imagine that you have a really complicated robot arm and that you need to, so like, look at how I'm going to show you this slide here. So here I'm actually, sorry, just a second. So if you look at the bottom right here, I'm actually using my whole body to basically give a demonstration to the robot, right? And you can't expect every person to be able to do this unless they're contact improv dancers, maybe. So anyways, I think in general, demonstrations can be hard, and finding different ways that you can actually achieve these initial demonstrations is helpful. But I do agree that typically a demonstration of any form is helpful. Demonstrations are typically kinesthetic, right? But I argue that we could also use different ways of demonstrating that are very different. So we can use, for example, dancers and choreographers. Choreographers demonstrate something, but they demonstrate it in a way that is a representation of an actual thing. So as a ballet dancer, I can demonstrate with my hands, but you know how to do it with your whole body because you have some domain knowledge. So maybe the way that demonstrations would be made more natural is through finding latent spaces and simplifying the demonstration so that you can transform the social signal that is easy for people to do into maybe a more complex piece of information that the robot can use.
So that's the thing. So so you're saying that you would use these alternative modalities like a feedback for the robot when it's trying to perform something that has learned
refine the behavior. Yeah, so those are refining the behavior. So those on the right here, the gestures and the speech is to refine the behavior. So whatever I taught you, make it a little bit more to the left, a little bit more to the right. This one here, for example, on the right side, is actually, the robot is performing the gesture and the person is intervening. Kind of like when you have, a parent and a child, and the child is doing something like cooking, and the parent is coming and kind of correcting a little bit, right? So yes, those are mostly for refining than for demonstrating.
Okay, thank you.
That's a very good question, thank you.
You're welcome.
Thank you very much. Unfortunately, our time has ran out. So if you want to continue talking with Kim, I bet he's most welcome to answer your questions in the Slack channel. So if you are not in the Slack channel, I think a link will be in the chat now. So don't worry about it. And you can ask Kim or talk about his work. Or if you're a future PhD student interested in living in Amsterdam, I think Kim would be much happy to talk with you. So once again, Kim, thank you very much for your talk. I would just like to share my screen for just 2 seconds of your time. And I would like to introduce the next speaker, which will be in 2 weeks. It's going to be Ross Smith. So Ross is the CEO and founder of Semio, and he's going to be talking about how to bring robots to life. So it's going to be a very interesting talk if you are interested also in the industry side of robotics. And it's going to be on the 19th of March. So to end this session, I would just like to thank you all for attending. If you want to, please support us just for infrastructure course at the Buy Me a Coffee. The link will also be in the chat. And having said that, have a nice weekend. And
thank you so much.
Thank you. Have a nice evening.
Thank you, everyone.